bit is just that all your matrices have become twice as big. So numerically that is about it. And then the discussion is about how to set up the H matrix, how to set up the sigma matrix, etc. But it's really, but otherwise it's all the same equations, nothing's changed at all. So, but to understand the physics, there's a lot that one can discuss, and that's what we'd like to talk more about and look at a couple of simple problems on how to do this. Now, the basic idea, which I often stress, is something like this: that the nearest thing I know to this electron spin, the nearest analogy, if you're not familiar with it, would be the polarization of light. That is, you think of it as light, photon polarization. That's this vector that tells you the direction of the electric field. And when you have a electric field in some direction, that's this polarization. So let's say I have a normal and have a vector in that direction. Then you can write it in terms of its z, x, and y components. And if this angle is theta and this angle is phi, could you help me with what the components are? The z component would be cosine theta. This would be sine theta cos phi. So this would be the standard thing you learn about vectors. Now, if you had a spinor with the electron, spin is pointing in this direction. It has an up component and a down component. There's only two components. And those two components are actually cosine half theta and sine half theta. And what about the phi? They enter as a phase factor here. This is phi. So this isn't very obvious, of course. Just stating it for the moment, and we'll try to talk a little bit about the consequences of this. But this is the basic result. Almost that if you remember this, and everything kind of follows from there. If you accept this, but this isn't obvious at all. But the way people visualize spins is just the way you visualize vectors, like it's pointing in some direction. But the components of the spin, there's an up component and a down component. And with vectors, you have three components, and they're all real. With spinors, you have two components, but then they're complex. So, for example, if you have a wave function that looks like, let's say, so supposing you have an electron whose spin is pointing in this direction with angle theta and phi, then these would be the components. So if you had a spin that was pointing along z, along the z direction, could you help me with what the up and down components would be? If it's pointing along the z direction, it means theta is 0. So cosine 0, that's 1. So it's only got an up component. That sounds right. This is 1. So that's something that's pointing along the z direction. If it is pointing along the negative z, that would be 0, 1. Now, what if it was pointing along the x direction? This is it is along the x direction. What is theta? 90 pi over 2. And phi is 0. So what would the x component be? 1 with a 1 over root 2 inside. So this is kind of illustrates the central point that when an electron is pointing along x, that's like actually a superposition of upspin and downspin. So just as with vectors, you could have vector in this direction, a vector in this direction. Those are the two orthogonal directions. And when you are 45 degrees, you are like this. This is 1 over root 2 of this, 1 over root 2 of that. Right? That's this elementary vector resolution that you learn. With spinors, it's like all the angles are doubled. There's the up and then there's the down. And those are the orthogonal directions, up and down. And if something is in between, that's like 1 over root 2 of this and 1 over root 2 of that. That's the essential. And often I say that, well, one direct experimental consequence of this, in the context of spintronics, most people would say that one of the most important results that kind of got the field started in the late 80s was this experiment, the GMR experiment, which I guess looking back now, you could say the essential point was this. If I take a device and I have two contacts, which are magnetic contacts, and the two magnets are parallel, looking in the same direction, then the resistance I will get, that's the resistance of parallel device, will be less than the resistance of anti-parallel. In fact, if you had perfect contacts, so the way you understand this is that when you have a magnet that's pointing in this direction, it has a relatively low resistance to upspins and a relatively high resistance to downspins. And with perfect contacts, actually, you'd like this resistance to be infinitely large, which means if it's a magnet like this, it only injects and detects upspins. That's the ideal. That's what we call a half metallic contact. And that's what people are striving for with Heisler alloys and so on. And if that were the case, then this would have been, the resistance would have been like infinite for anti-parallel. We can talk a little more about that. But the point I make is that this is a little bit like the freshman physics experiments with polarizers and analyzers. How does that work? Well, you have a polarizer, let's send photons with a particular polarization. And if your analyzer is in the same direction, light goes straight through. That's like a low resistance. If they are 90 degrees, then this will block everything. It doesn't go through. With electrons, though, you'll notice it's a little different. It's like, you can think of these as polarizer and analyzer. But here's the polarizer. And of course, if they're parallel, that's the low resistance. Electrons flow right through. But the way you block it is not by going at 90 degrees, but by going at 180 degrees. It is the anti-parallel one that is the high resistance. That's all. So when the two magnets are anti-parallel, that's when you will have the high resistance. Unlike light, where the high resistance would have been when it was 90 degrees. And that is almost a direct consequence of the fact that this is theta and this is half theta. Okay? Direct consequences of the half. Okay? Now, of course, something like this has, there's all kinds of tricky issues, subtle issues involved. Because one thing you would say is, if I take something pointing in this direction and I turn it around by 2 pi, 360 degrees, it's still the same thing, pointing in the same direction. And here, of course, that works fine. If I add 2 pi to that, nothing's changed. Cosine, all the angles add 2 pi, no big deal. But here you'll notice if I add 2 pi, it has consequences because it's half of that. Right? Now, in practice though, that causes no real problems, because you might say, well, then how do I know the sign of anything? Because if you go around 2 pi, it's the other thing. But makes no real difference, has no real problems, because here we are talking of electrons and the observable quantity is the psi dagger. And that one is not affected. So even if the psi picked up a minus sign, observable quantities wouldn't be a problem, because all observable things would have a psi side, would both have both of those. With photons you would have got into trouble if that was the case. Right? Now, so one thing that is instructive to look at is what psi dagger would look like. Remember, in doing this NEGF method, I defined Gn. I guess there was a 2 pi involved, but other than that, there's this psi dagger. So we could try doing that here. So maybe let me just call this C and call this S. So psi is like CS, psi dagger is C star S star. So you'll notice, so this is a 2 by 1 column vector. This is a 1 by 2 row vector type of thing. So when you multiply it, you get a 2 by 2 matrix. So what's this component? CC star. And that is how much? Magnitude of C. So that's like cosine squared half theta. Cosine squared half theta is half of 1 plus cosine theta.